The operations process chart represents the core of your manufacturing system because that's where you're adding value. And so that's where you will invest your time, your money, your efforts in order to maximize the value and minimize the cost per part. But that doesn't tell the whole story because we haven't addressed a significant issue, which is material flow through our system. How does that happen? Well, the only way that's going to happen is if we have the necessary elements that describe the flow and how it will occur as production occurs. So we have a material flow process chart, which is essentially a further elaboration of the operations process chart. And here we're going to add those material handling elements that will support the material flow. And of course, what happens when material stops flowing? We're going to have to store it somewhere. So we need a storage location and perhaps a more sophisticated way of storing material in terms of storage structures. In order to accommodate material handling, we're going to transfer or transport material. And sometimes we will have delays as the material flows. Typically, those delays are going to occur when you're waiting for something. The way we represent the material flow elements is, first of all, a storage is an upside down triangle here. S-1 would indicate a unique number for an area where we will store material. And then T-1 represents a transfer, so material is actually moving from one location to another. And of course, we would describe the type of device that we're using in that transfer. And then these unexpected delays where we are waiting for something else, trying to synchronize, will indicate with this shape, this D shape, and identify it as D dash and then the unique identifier. Again, we would want some kind of description here informing us as to why this delay is occurring. The operation, again, just for review, represents some type of value adding. That's the core of the manufacturing system. Your transfer, transportation, again, moving from one location to the next. Inspection, verification that your value adding operation was successful. Delay, the next action is waiting for some condition. And then we have an object sitting in storage. Note that out of all of these, we have 4 types or 4 classes of non-value adding. Again, the circle only represents those processes where we are adding value to the product. So in transportation, you can think of moving by either manual methods, and that can be any type of moving. Typically, you are going to another workstation, so we're not going to describe movements within a workstation, but what happens when we move to the next step in our process. So it could be by hand, it could be by fork truck, it could be by overhead crane, whatever mechanisms we're using to transfer material through our system. The delay, we think of waiting for processing, and again, when we do a delay of some kind, that delay is based upon waiting for or synchronizing with something else. So here we're waiting for an elevator. Again, there's some condition under which we will wait or be synchronized with that element in our system. Or in this case, papers waiting to be filed, essentially waiting to be synchronized with an operator. So you're not going to put this in front of every operation, but only those that require some type of synchronization. Storage, of course, can take a variety of forms depending on the nature of the material, anything from racks to bins to super sacks to storage in trailers. There's all kinds of ways in which we can store material, both on the production line, in special storage locations throughout the facility. Essentially, what we're incurring here is some type of short-term or long-term holding costs because the material is not being processed through an operation. It is just sitting and waiting for use. When we do assembly, we'll often indicate that with the letters SA for subassembly, and then our final assembly, representing our final product, would be indicated by just an A. Again, this is just a way to be more informative about the operations in our material flow process chart. Of course, after final assembly, we might do some finishing operations, packaging, and so forth that would follow our final assembly. So our structure of the material flow process chart again looks like a tree with branches going out, starting at some initial stock material. So here we have our stock material, and ending up with our final product, perhaps going into the shipping area. Of the total time our product spends in the facility, the big question we always have is what percent of that time is value adding? And of course it varies from industry to industry, but you might be surprised to find out how small a percentage of the time is actually spent in our core operations. And that's really because of these other elements that we've added, the storage, the transfers, the delays. They represent a significant portion of the time. Of course, you would like to maximize this percent of time that's value adding, which means these elements we've added to provide material flow need to be addressed, as well as the operations where we're adding value. You might also see a material flow process chart in this type of table configuration, where essentially we'll trace what is happening in this column of symbols, just drawing a line segment from symbol to symbol, indicating that we have various elements occurring as we move through our system. Here we provide a description of that particular element and what is happening there, and we can add an estimate of time. So we get an overall estimate of time that it takes for the material to flow through our system. If I add up this column, you should realize that this represents our manufacturing lead time, the time it takes to get through our manufacturing system from beginning to end. Now that we have a material flow process chart, that becomes the basis of all the elements that we need to put into our system in terms of workstations, in terms of storage systems, and material handling systems. So then you begin to ask the questions related to our process planning. If I look at those operations, what tools, jigs, and fixtures are required in order to make that operation successful? And you have to consider simultaneously what would help you decrease your cycle time and therefore make your system more responsive, because that will affect your manufacturing lead time as well as your production rate. What will help you reduce the process cost, in other words, dollar per part, that we saw when we estimated the cost per part. And of course, we're always concerned about factor S, which has a profound effect upon the cost, upon our ability to satisfy the customer demand. So let's look at a couple examples here. Here we've got a winemaking process that is based upon a chemical reaction, which, if you look at that, is the basis of ethanol production for biofuels. Here we take a sugar, glucose, and yeast and ferment that mixture. We end up with a byproduct, ethanol, as well as carbon dioxide. So if we look at this process, we have to think about where are we adding value, and that would be the basis of the operations process chart, our core, and what is the direct material involved in this product. So here's the process description. What we're going to do is take grapes, And that's where we begin. We gather grapes, load them into a wine press, and they're going to be squeezed for about 120 minutes. After squeezing, the juice that comes out will be pumped into a storage tank, and there the temperature is going to be lowered. So there's some type of temperature control here, and the sediment in that juice will be separated by gravity, so it'll fall to the bottom of the tank. The pumping takes about 90 minutes into the storage tank. After 3 days in the tank, the juice is going to be pumped into a fermentation tank, and that also takes about 90 minutes. To that fermentation tank, we'll add yeast, and then a water trap is used to prevent air from entering the tank. So, of course, CO2 can exit through the water trap, but air from the outside cannot enter. After 14 days of fermentation at a constant temperature of 78 degrees, then we pump the wine, the fermented mixture, into a separation process where the yeast and sediment are going to be removed. This process usually takes about 140 minutes, and then what we'll do is meter out wine into individual bottles, insert a plastic cork, and then apply an adhesive label to the outside of the bottle. The tanks used in the process hold enough wine to fill about 5,000 wine bottles. So you get an idea of what's happening in the system. Then the question is, what does our material flow process chart look like? And of course, you always want to begin by identifying the direct materials. And so you should be able to, based on this description, you should be able to readily identify what is direct material and what is indirect. So as a first step, we might do an operations process chart here. And we've got our grapes, which are obviously direct material because we are extracting the juice from there. And what I'm going to show here is some material that's leaving. Now, we wouldn't normally do that. Essentially, this is the waste stream, just so that we can account for all the direct material. This line here between O1 and DA-1 represents the juice with the sediment in it. So clearly the material here is not the same as the material entering this process. So of course we are adding value by extruding the juice. Then in the sediment separation, which we said was about 4,300 minutes, the sediment is going to settle out and therefore become part of the waste stream. Then we go through fermentation. Again, this material entering here is not the same as the material exiting fermentation because of the chemical reaction. And then after fermentation, we said that we're going to separate out particulates. And so again, we have yeast and sediment exiting. The question is, why doesn't the yeast enter in as direct material, even though we're showing it leaving that process? Well, that's because, again, the yeast is not direct material. It's indirect. It's not something that we want sending to the customer in terms of being in the wine at the end of our production. And so yeast would represent indirect material. You can kind of think of it as tooling. After we separate the particles, then we have our wine that needs to go into bottles. And of course, you should recognize that the bottles themselves are direct material because they will end up going to the customer. So the bottle enters our operation here. We have a subassembly going on, the wine and the bottle. After we fill the bottle, then we have another subassembly, the cork. We insert the cork. Again, you should note that the material entering that operation is different than when we exit. And then the final assembly, we apply a label to the bottle. So we understand the core operations where the direct material is entering into our system. Now, what does the material flow look like? Well, we did have some transfer operations, and here we can see the pumping of the juice that was extruded occurs, representing a transfer from the wine press operation into the storage tank where the sediment separation will occur. And then we have another pumping operation that was specified between the two storage tanks. So at this point, this is all that we have in terms of our description. Now, we might consider having also some type of transfer for the bottle, or we could perform all operations at the same workstation. It depends upon how we want to set up our system. So we could add additional transfers at that point. Let's look at another example. Everybody loves pizza. So what happens when you order a pizza and you expect your delivery within 30 minutes or less? Well, we need a system to create that product within that time window. So if we look at this system, we're going to need some basic operations that form the core in terms of adding value that the customer wants. Initially, what we'll do is we'll mix the dough based upon 4 direct materials. Note that in this context, we have this perhaps the same material, the yeast, but now it's direct material because it will end up in our product. So in this context, it would be direct. We mix that, create the dough, so this material coming out is different than what entered. And then we're going to do a disaggregation process in terms of dividing it into different sizes. And then there will be a modification of the material by letting it rise. And then we'll modify the geometry by creating a shell. Finally, we'll spread the sauce, which is a subassembly, add cheese, again a subassembly, toppings, our final assembly, and then we'll bake, which represents a material property change. We will cut, again we are actually changing the material properties of the pizza, and then we'll do another assembly. We will place it in a box, our package, and then it's ready to deliver or be picked up by the customer. So you should be able to identify, in this case, the direct material that's entering the process, the box, the food ingredients, and now we understand our core system to create this product. Now there's some challenges in the system in that if you look at the operations here initially, this actually takes a significant amount of time, and therefore if the expectation of the customer in terms of manufacturing lead time is 20 to 30 minutes, we're going to have a problem here due to the time it takes for the material properties to change and of course mix and divide into the different sizes. So we'll have to take that into consideration when we add the elements for material flow. Well, we could, after we go through the mixing operation, then we might move to the counter, another workstation, where we divide it into different sizes and then let it rise. And now you see I've added a transfer operation where we're going to move that material in its current state to the refrigerator. And the goal there is to prevent changes in the material property. So I transfer it to the refrigerator where it is stored. So S-1 represents the actual refrigerator, and we are waiting for an order. Now, we might think that this violates the whole premise of just-in-time production because we're producing a significant number of material in terms of dough, batches of dough, that are sitting in the refrigerator. This needs to be done in order to achieve the necessary manufacturing lead time. Otherwise, we're going to end up with orders taking hours to prepare, and then you won't have any customers. So this is a critical step in our material flow, but it is intended not to be value adding. Now, of course, there could be some changes in the properties of that dough, but it's not going to be significant, and therefore we wouldn't consider it to be value adding. It is critical that we have this step in our material flow, otherwise our system will fail. Well, once we get an order, we're going to remove that material from the storage, and then we'll create the change in geometry in terms of the shell that will be the base of the pizza. Once we have the shell created, and note what the effect is of that storage, essentially our process from what the customer perceives entails just these operations and transfers. And therefore, it gives the appearance to the customer that this is all that's required in terms of manufacturing lead time to produce a product. And now we spread the sauce, cheese, toppings, move into a staging area, and then we're going to wait for oven space. And that's, of course, because we have limited capacity in the oven. Then we transfer it to the oven, bake, and then move to a cutting area, and finally cut, and then place in our box. And then it's ready to go to the customer. Now you should be able to create alternative systems. This is not the only feasible configuration for our system, but it is a feasible system that would produce product in a reasonable amount of time for the customer. So in summary, again, values being added when geometry or material properties are changing during the process. Those elements represent our operations. Operations are value adding. All other nodes in this system architecture are non-value adding, but as we just saw in that previous example, those can be critical steps in our material flow in order to satisfy customer demand. Key concepts here: material flow chart. You should be able to create that material flow chart based upon what needs to occur with our direct material flowing between our operations. By adding additional elements, the transfer, the actual motion of the material, the storage of the material, and potential delays in our system, we get a much better idea as to what it takes to produce a product in terms of our manufacturing lead time. So material flow process chart integrates subsystems, the material handling systems, the storage systems, and those can be critical to our overall success. Material transfer requires some type of material handling equipment, whether it's a hand cart, a pallet jack, fork truck, overhead crane, conveyor, whatever the device is, we're going to need to factor that into our system, and of course, its effect on the cost per part. Storage, of course, will require space, and also storage equipment in terms of racks, automatic storage and retrieval systems, but there does have to be space available and sufficient space that we'll talk about later when we get to that point in our development process.